Lesson 6.6 is exponential decay, which is very similar to exponential growth, but in this case, instead of going up and up and up and up, we're going to be going down and down and down and down, which is why it's called decay. So the learning goal for today is I will identify exponential growth and decay, and I will write, interpret, and graph exponential decay functions. So that's what we're going to be focusing on for this lesson. Starting off, we need to look at what our basic exponential decay function looks like. So it's going to be very, very similar to our exponential growth function, except for, in this case, instead of adding the growth rate, we're going to subtract, because this is the rate of decay. And again, that's going to be in decimal form. So y is still your final amount. A is your initial amount, or however, if it's a population, what you're starting with. In this case, R is called our rate of decay. And again, it's in a decimal form. T is still representing time. And then before, this was called the growth factor. But now instead of growing, we're decaying, so this is called the decay factor. So for exponential decay, this number in here is going to be less than 1. It's going to be between 0 and, it's going to be between 0 and 1. So that's what's going to make our exponential functions decay or decrease instead of increasing, because with growth, we were adding here, so our growth factor was always more than 1. So to start off with, we're going to look at some tables and decide if they're showing exponential growth or decay, or neither. So our first table, we have our x values and our y values. We have 0, 1, 2, 3, and 270, 90, 30, 10. So the first thing that we want to look for is to see, make sure it's not linear. Here I'm dropping by obviously different amounts every time for every increase in 1 for my x value. So it's obviously not linear. We also see that as my x value gets greater, my y value gets smaller. So it's obviously not going to be an exponential growth situation. So then what I want to check for is, am I decreasing by the same factor every time? So to go from 270 to 90, notice that 90 is 1/3 of 270. If you thought about that as 9 and 27, 9 times 3 is 27. So to go this way, I'm multiplying by 1/3, because 90 is 1/3 of 270. In the same situation here, 30 is 1/3 of 90. So I'm multiplying by 1/3. 10 is 1/3 of 30. So I'm multiplying by 1/3. So as x increases by 1, y is being multiplied by 1/3. 1/3 is less than 1. So this is going to be a decay function. If we look at another table, we have our x and our y, and let's say 1, 2, 3, 4, and 4, 12, 36, and 108. Again, you can see really quickly that it's not linear because I'm not just adding the same thing each time for y. So my next thing to check for is that I'm increasing, and to get from 4 to 12, I multiply by 3. To get from 12 to 36, I multiply by 3. I multiply by 3 to get 108. So this is going to be an exponential growth function because to go from one term to the next, I'm multiplying by a number that's greater than 1. So this is going to be exponential growth. So it's pretty obvious just by looking at the tables if it's going to be exponential growth or decay. Just remember that you need to be multiplying by the same factor every time. Okay, now here's a chance for you to do a quick on your own problem, actually 2 on your own problems. I want you to determine if these are exponential growth, decay, or neither. So pause, work that out, and then hit play. Okay, for number 1, we can see that my x is increasing by 1 each time, so that's a constant rate. My y is decreasing by not a constant rate. You know, this is 3, this is 12. That's not constant, so it definitely can't be a linear function. But I'll notice as I go this way, I'm multiplying by 4. So to go from 64 to 16, I need to multiply by 1/4. To go from 16 to 4, I multiply by 1/4. To go from 4 to 1, I multiply by 1/4. 1/4 is less than 1, so this is going to be exponential decay. I'm multiplying by the same factor each time, and it's less than 1. If I look at number 2, you'll see that the x is actually changing by 2 each time, and that's okay. That's still a constant rate. So that's not necessarily what the problem is here. But as I go from 4 to 11, and then 11 to 18, 18 to 25, I see that I'm actually only adding 7. And remember, if you're just adding the same thing each time, this is actually a linear function. That's not going to be exponential growth or decay because we're just increasing at a constant rate. So that is how you're going to do those. For example 2, we have a story problem. The function p equals 5,100 times 0.95 to the t power represents the population p of a town after t years. By what % does the population decrease each year? So we know that this is exponential decay because my number in parentheses, or this factor here, is less than 1. So that's a decay factor. And remember, our decay factor looks like this, 1 minus r. And we know that that equals 0.95. If we think about this as a percent, what this is saying is that every year, 95% of the population is sticking around. So if 95% of the population stays, or the population rate, or the actual population is at 95% of the year before, then we must be losing 5%. So you could set it up like this and solve by subtracting 1 from each side and take the opposite, or you can just think about it logically. If 95% stays, then 5% must be leaving. So the population is decreasing by 5% each year. So if you were given this story problem set up a little bit differently, and they said you have a town that starts with 5,100 people, and the population is decaying at a rate of 5% per year, you would put this 5% in for the rate. So an on your own problem for you to try quickly. You have this function, a equals 275 times 9/10 to the t power. This represents the area. The A is the area of a coral reef after t years. So what % is the area of this reef losing each year? So pause just for a second to think about it, and then come right back to me. So if our growth factor is 9/10, another way to think about that is 90%. So 90% of the coral reef is staying. That means you're losing 10% of the coral reef each year. So the area of the coral reef is decreasing by 10% each year. Here's another story problem where we're not actually given the equation, so we're going to have to come up with the formula. So the value of a car is $21,500. It loses 15% of its value every year. We need to, A, write a function that represents the value, y, in dollars of the car after t years, and then we need to graph the function from part A and use that graph to estimate the value of the car after 4 years. So the key word here is that it's losing 15% of its value each year. So if we're using our exponential decay function that looks like this, our rate of decay is 15%, or 0.15. A is our starting value, which is $21,500. And then Y and T are what we're going to leave as our independent and dependent variables. So that means Y equals 21,500 times 1 minus 0.15 to the T power. If you think about this, if you're losing 15% of your value, you're keeping 85%. So to simplify, when I do that 1 minus R, I get 0.85 to the T power. So this is our simplified function right here. And then we're asked to graph that function and use the graph to estimate the value after 4 years. So of course you could put 4 into this equation and you could just see what you get. But we can also graph this, and I'm going to graph it on my calculator. So I'm going to say Y equals, let's turn that off. Y equals 21,500 times 0.85 to the X. And I'm going to use X as my independent variable. That's just how these calculators work. So when I first push graph, oh, that actually did show up. My window is really crazy right now. So if I'm thinking about what's happening here, my time, I'm talking about years. I want to estimate the value at 4 years. So let's just think about our time, or our X, as going from 0 to 10 and counting by ones. So we'll have a dash every 1. And then for Y min and Y max, we know the car is starting at $21,500. So let's start at maybe 23,000. And let's just go down to maybe 10,000 and count every 5. Let's just see how that looks. There you go. So that gives me a pretty good graph where this is my time, this is how much my car is worth. So what I can do is I can push this button right here that says trace, and that's going to follow along on my line. You can see, like, that's about a half a year. The car is going to be worth $19,719, and it can travel along and give me different values. But you'll see that it doesn't give me 4 exactly. So what I can do is I can just, when I'm in the trace mode, I can just push 4, enter, and there you go. When X equals 4, Y equals 11,223. That's not really an estimate. That's pretty exact. But if I were to sketch this out on a piece of paper, maybe I would just pick a couple of points. I would see, when X equals 1, when X equals 5, and kind of sketch that out. And then I could make an estimate. I'd probably guess around 11,000. But this is one way you can use your calculator to help you with the exponential functions. So this was an exponential decay function, remember? We knew that it was decay because it was losing 15% of its value. So that 15% is what we put in for R. So this is the whole idea behind exponential decay.